Welcome back to the second portion of section 2.8. Our focus will be on predicting products of single replacement, double replacement, and combustion reactions. We're going to start off with a single replacement reaction, and in order to predict those products, you have to use an activity series chart, which is simply a chart that shows the reactivity of metals and halogens. You can see it off to the right, and we're going to actually focus in on the activity series of metals right now. But it's actually found on your reference sheet, so there's no memorization here. You just need to be able to use it and then apply it in the prediction process. So the first thing I want to tell you is that elements at the top are more reactive than elements at the bottom. And when you're doing a single replacement, more reactive elements can only replace less reactive elements within a compound. So for example, lithium could replace calcium in a compound. Calcium could replace zinc in a compound. Zinc could replace nickel in a compound, and so forth. But bismuth could not replace chromium in a compound. Now, the other thing I want to point out to you is that there is a hydrogen kind of stuck in between this list of metals, and of course hydrogen is a nonmetal. We are going to have special rules when we're trying to replace a metal with a hydrogen from water. Okay, and you can see those off to the side over here, or when the metal is trying to replace the hydrogen from an acid. Right now, all you basically need to know is that any of the metals above can always replace a hydrogen from an acid, and that there are 3 tiers before we hit hydrogen, and they have special guidelines that will help you determine whether the hydrogen can be replaced with the metal or not. The last thing I want to point out is that at the top there is also a second chart for halogens, and the same rules apply. Fluorine can replace chlorine, but iodine cannot replace bromine. All right, this self-check is one that I would lead you through. We're going to determine if the following replacements can happen. We're going to use the activity series to the right. There are actually 4 single replacement models. We're going to focus in on the first 3 in this self-check. Metals replacing metals, like we see in example 1 and 2. A metal replacing a hydrogen in water, like we see in examples 3 and 4. Or a metal trying to replace a hydrogen in an acid. So if we take a look at the first example, potassium is trying to replace calcium. And if I find potassium and calcium on the chart, you will see that potassium is sitting above calcium, and that reaction can occur. If we take a look at the second example, you will see that copper is trying to replace zinc. Copper is way at the bottom, zinc is somewhere in the middle, and when you're below, you are less reactive, and that will not occur. And so that one will not react. If we take a look at the third one, you will see that it is a metal trying to replace a hydrogen. Now that's water, and here's the hydrogen down here, and you'll notice that every one of these metals is above it. However, there's special rules for when a metal wants to replace water. The first tier will replace hydrogen from cold water and warm and hot water. So it actually replaces at all temperatures. In the second tier, these metals will replace hydrogen only from steam. And the way that we can tell steam in a chemical formula is by looking for the little G that stands for gaseous. In the third tier, we're just going to find out that even though these elements are sitting above the hydrogen, they will not replace the hydrogen. Okay, so that's kind of a catch right there. So when we take a look at sodium, sodium is right here. Hydrogen is down here. We know that sodium is above it, so we would think it would react. It's also in that first tier, which means that it can replace at all temperatures, and so this reaction would definitely take place. But when we take a look at number 4, where we're looking at nickel, even though nickel is sitting above the hydrogen, it's in that third tier, and it will not replace the hydrogen. The last thing we're going to look at is when a hydrogen can replace, or a metal can replace the hydrogen from an acid. And the only thing I want to point out to you here is that magnesium, and there's your hydrogen down there, is sitting above it. And in fact, if you look at this statement right here, any of the metals in tier 1, 2, or 3 will always replace the hydrogen from the acid. So where magnesium is prime for that replacement, and so we're going to check that off. Let's take a look at Model 3A of single replacement reactions, where a more reactive metal replaces a less reactive metal. You can see that the metal and the ionic compound are reactants, and since metals sit in the front, A is going to try to push out B. If the activity series says it can happen, then B will get pushed out, and A will form a new compound with C. So how do we predict those products? Well, you're going to use your activity series chart to see if the single metal is more reactive than the metal in the compound. If it is, you're going to replace it and check the charges of the new compound. And we also want to be on alert for diatomic elements. If, however, the reaction cannot occur, we will write an R on the product side. Let's take a look at this example. We've got zinc, which is a metal, trying to replace copper, which is a metal. And if we look on the chart, you can see that zinc and copper are in their respective places. Zinc is more reactive than copper, so this reaction is going to take place. So I'm actually going to take the zinc and I'm going to put it next to the NO3. Now by now, hopefully you have realized that we don't usually take subscripts with us, we just take the symbols. But since NO3 is a polyatomic ion and it acts as a single symbol, we have to take that 3 with us. And then I'm going to kick out the copper. Okay, copper is not diatomic, so I don't have to worry about it, but I do have to check the charges of zinc and nitrate to see what kind of ratio they need to be in. And in this case, we find out that they need to be in a 1:2 ratio. Now we're ready to balance, and if I look at this very closely, I will notice that I have equal numbers of atoms on both sides, and so we don't need to do anything else with this example. Alright, so this is Model 3B of single replacement reactions, where a more reactive metal replaces hydrogen from water. One of the things that we want to do initially in this type of example is change the water H2O to HOH, because when the metal replaces the hydrogen, it actually forms a metal hydroxide, okay, and hydrogen gas. Of course, we're going to do this the same way that we did in the last problem. We need to consult the activity series chart. We're going to head on over to the chart, find sodium and find hydrogen. We spoke about how water has special rules. Since sodium is sitting in that first tier, it will always replace the hydrogen. I'm going to rewrite this as HOH, and as this sodium replaces the hydrogen, it will form NaOH, which is the base, and then the hydrogen gets kicked out. It's diatomic. I do need to check my charges on this, but they both have a +1 and a -1 charge, which neutralizes, and they're happy in a 1:1 ratio. The only thing I have left to do here now is to balance this, and so I will need to put some coefficients. The sodiums and the oxygens are equal on both sides, so I have to focus in on the hydrogens. And I'm going to give you a little tip here. When you have an even number of hydrogens on one side and an odd number on the other, I have 3 over here, try to make the odd number even with the lowest even coefficient, which would be a 2. So when I do that, it changes my hydrogens to 2, and 2 is 4, and that means I can put a 2 here to get 4 hydrogen. That means I now have 2 oxygen, and I have 2 oxygen, 2 sodium, and so I'll have to put a 2 in front of the sodium as well. And now it's balanced. Okay, if we take a look at the second example, okay, you will see that aluminum is trying to replace the hydrogen in water, and this time aluminum is in the second tier. Remember that these elements can only replace hydrogen from steam. Since I didn't acknowledge what state of matter this is, we're going to say that this reaction cannot take place, that it is just plain old room temperature or cold water, and we're going to write NR for no reaction. Model 3C of the single replacement reaction series is when a more reactive metal replaces hydrogen from an acid. You can see in this case the metal is going to try to replace the hydrogen. If it can, it will make an ionic compound, and then the hydrogen gets kicked out. Of course, it's diatomic, so it gets that subscript of 2. We're going to do the same thing we've done in the last 2 examples. We're going to check the activity series chart to see if it can occur. If so, we replace it and check the charges, and then add the hydrogen. If not, we write NR for the reaction. So let's go ahead and take a look at magnesium and hydrogen, and you'll remember that with acids, any metal sitting above the hydrogen can replace. So magnesium is sitting above, so magnesium is going to take the place of the hydrogen. We'll get MgCl. Hydrogen gets kicked out, it's diatomic, and then I do need to check my charges on my ionic compound. By crisscrossing, I'll realize that this needs to come together in a 1:2 ratio. Now all I have left to do is balance this chemical equation. And so I notice I've got 2 chlorine on the right, so I'm going to put a 2 on the left. That gives me 2 hydrogen. I have that over here. And my magnesiums are balanced, and now I'm finished. Right, and the last model, 3D, is when a more reactive halogen replaces a less reactive halogen. Now we're actually going to focus in on this activity series chart. And remember that a halogen is a non-metal. Non-metals actually sit at the back of an ionic compound. So D is going to try to replace C, and if it can, we'll get the ionic compound of BD, and C will get kicked out. Most likely this will be a diatomic element, and we'll have to put the subscript of 2, but sometimes that's not the case. We do the same thing as before. Check the activity series chart to see if it can occur. If it can, replace it, check charges, and if not, write NR. So if I take a look at this single element, I notice it's not a metal. This is the first time we've seen this. It's a halogen. It's a nonmetal. So we want to go to the compound. The only model we have is a halogen replacing a halogen, and find the other halogen or nonmetal in this case. And we'll go to the top and see, can chlorine replace bromine? It can. And so this chlorine is going to sit in the back of the compound. Be careful with this. The K comes first, then the Cl, and then we kick out the Br. Of course, bromine is diatomic, so I'm going to give it a subscript of 2. I am going to check my charges. They will neutralize in a 1:1 ratio, so I don't need to do anything to this chemical formula. And now I'm ready to balance this. And so I notice that I have 2 bromines on the right. I'm going to put a 2 here, and that gives me 2K. So I'm going to put a 2 here. That gives me 2 chlorine, and I have that over here, and now it's balanced. The solubility rules chart is the second chart that you need to be comfortable in using, and it classifies substances as soluble, meaning that the substance can dissolve in water, or insoluble, meaning that the substance will not dissolve in water. Insoluble substances are also called precipitates. The solubility rules chart is found on your reference sheet, and it's categorized by anion. So let's take a look at the example at the bottom. You'll notice that there are 2 sides, the soluble side and the insoluble side. And the insoluble side is basically the precipitate. So basically how you read this chart is you're going to look at the statements. Statement 1 says all nitrates, acetates, ammonium, and group 1A ionic compounds will always be soluble. The second bullet says that chlorides, bromides, and iodides will be soluble, except silver, lead, and mercury. Okay. The third bullet says that all fluorides are soluble. Once again, there's an exception. Group 2A, lead 2, and iron 3. Every time there's an exception, it pushes it over to the right and makes it insoluble. The last one says all sulfates are soluble. Once again, except calcium, strontium, barium, mercury, lead 2, or silver sulfate. In that case, those would be considered insoluble. If we look at the other side, these anions are usually insoluble. All carbonates and phosphates. But once again, there's exceptions. If a group 1A or the ammonium ion is connected to a carbonate or a phosphate, then it pushes it as soluble. Normally, hydroxides are insoluble, but group 1A, strontium, barium, and ammonium attached to a hydroxide would make it soluble. All sulfides are generally insoluble. Once again, if a group 1A metal is connected to a sulfide, it then becomes soluble. And lastly, all oxides are generally insoluble, but if a group 1A is connected to it, then it becomes soluble. So we're going to do a self-check, and I'm going to actually lead you through this self-check again. We're going to use the solubility rules to determine if the following substances are soluble or insoluble. So you're always going to look for the anion. I'm going to look over here, and I see chlorine. Chlorine is a chloride, and it says that all chlorides are soluble unless silver, lead, and mercury. And since calcium is not silver, lead, or mercury, we're going to say that this is soluble. We take a look at the second example. My anion is phosphate, and phosphate is over here. So that's on the insoluble side. However, K is a group 1A. It hits the exception, and that makes that soluble. So that will also dissolve in water. The next one is carbonate. Carbonate is on the insoluble side. Magnesium is not a 1A or ammonium, and so that will not be soluble. We're going to call that a precipitate. In question 4, we've got the hydroxide ion. The hydroxide ion is on the insoluble side, and zinc is not a group 1A, strontium, barium, or ammonium, so that's going to remain insoluble and will become a precipitate. Sulfate is on the soluble side, and it's not calcium, strontium, barium, mercury, lead 2, or silver, and so it will be considered soluble. And the last one is nitrate. Nitrates are always soluble. Alright, there's only 2 models for double replacement reactions. We're going to look at model 4A, which is the formation of a precipitate. Remember, a precipitate is the insoluble solid that is forming in this reaction. And the way that you're going to identify this is you've got 2 compounds. One or both will be aqueous, dissolved in water already. And the positive ions are basically going to swap places with each other. And so when A swaps places with C, it will then become AD, and then you will end up getting CB because C is going to take the place of A. In the formation of a precipitate model for A, one of these 2 will be a precipitate. You'll use your solubility rules chart to predict that. Remember, when you make these 2 new compounds, you will need to check the charges on them. So let's quickly do an example. So I notice I've got 2 compounds here. The sodium and the silver are going to switch places with each other. We're not using the activity series chart here. Sodium is going to sit next to nitrate. I had to take the 3 because it's part of the polyatomic ion. And then silver is going to sit next to chlorine. Remember, the positive ions are swapping places, so they should always be sitting in the first position. And I do need to check charges. Both the sodium and the nitrate have a positive 1 and a negative 1 charge, so those will neutralize, and so does the silver and the chlorine. So they are actually good to go, and now all we have to do is balance this. And the great thing about this one is it is already balanced. Now the last thing we have to do here is find the precipitate. And so we are going to look at the last part of each ionic compound, the anion, and we're going to find them. Notice that they're both on the soluble side, but remember, all nitrates are soluble, all chlorides are soluble except for silver. And so right off the bat, that tells me that's my precipitate. One of the ways that we can identify the precipitate is putting a little S for solid underneath it. In theory, everything else is aqueous. Okay, meaning that they have been dissolved in water. Our last double replacement reaction model is 4B. It's an acid-base reaction. The way that we're going to identify these is we're going to see the reactants are either acids or bases reacting with one another, and they will always form a salt, which is an ionic compound, and water. This is a double replacement reaction, so all you will be doing is swapping the positive ions like before. We just won't be using the solubility rules chart to predict a precipitate because there is not one. So let's go down to the bottom, and I will notice that this is my base and this is my acid. And I'm just going to go ahead and switch these guys. And so K is going to sit next to SO4. Now remember, the only reason why I'm taking the 4 is because it's part of the polyatomic ion. and then the hydrogen is actually going to sit in front of the OH. And of course, that's water. You can leave it as HOH, it might help you in balancing, or you can change it to H2O. I do need to check the charges on the new compound. Since K is +1 and SO4 is -2, that does mean that I need to put a 2 here. Okay, and now I'm ready to balance this guy. And so if I look at the subscripts for potassium, you will see that there's 2 on the right. I need to put a 2 over here to make those equal. That gives me 2 hydroxides. Over here I only have 1, so I'm going to put a 2 here. That then gives me 2 hydrogen, which I have over here, 1 sulfate on both sides, now makes it balanced. Notice that this is the salt, the ionic compound, and the water. There's no need to use the solubility rules chart. Our last reaction is a combustion reaction, and this is Model 5 on your reference sheet. It is when a hydrocarbon reacts with oxygen. Remember, the way that we can identify a combustion reaction is when we see oxygen as a reactant. Anytime a hydrocarbon, which is a compound containing hydrogen and carbon in various ratios, reacts with oxygen, it always produces the same 2 products of carbon dioxide and water. Let's take a look at the 2 examples below. You will notice both of them have a hydrocarbon burning in the presence of oxygen, and so it's going to be easy for me to predict the products in both of these examples, carbon dioxide and water. All that is left now is to balance these chemical equations. We're going to start off with the first one. With a combustion reaction, a lot of times it's easy to start with the carbon and then the hydrogen. Lastly, you will hit the oxygen. And that is because the oxygen is in more than one compound, so it makes it a little bit harder to do. So we have 3 carbons, so I'm going to put a 3 over here. I've got 8 hydrogen, so I'm going to put a 4 here to get 8 hydrogen. And by doing that, it changes my oxygen numbers to 6 and 4, which is 10. And I know that a 5 will get me to 10 on the other side. It's now balanced. Remember, you can leave that first coefficient blank, or you can place a 1 there. If we take a look at the second example, I've got 1 carbon and 1 carbon over here. I've got 3 and 1 is 4 hydrogen, and I only have 2 hydrogen here, so I'm going to place a 2 in front of the water. When I do that, it then changes my hydrogen to 4, and I have 4 over here, so that matches. Changes my oxygen to 2, and I have 2 over here, which gives me a total of 4. Now the problem is that on this side I have 2 and 1, which is 3, and that doesn't work out. So when you have situations like that, it's best to kind of just start over. And since the 1 did not work the first time, I'm going to go ahead and put a 2 in that first position and just modify from there. 2 carbon. I've got 6 and 2 is 8 hydrogen, so I'm going to put a 4 here for 8 hydrogen. And now I have 4 plus 4 is 8 oxygen. I have 2 oxygen already here, leaving 6 left over to make that 8, and so a 3 times 2 will give me 6. So in this case right here, the coefficients are 2, 3, 2, and 4. All right, this concludes predicting products, section 2.8. Lots of practice will be happening in class and hopefully at home, and much success will happen on the test. We'll see you then.